Through the previous proof, we obtain an equation which is corresponding to the number of equivalence class. It is actually situation. It can be solved by the number of all one-order cycles, then divided by all the number of permutations. Actually, this equation is Burnside Lemma. What does Burnside Lemma do? It is used to solve the coloring equivalent solutions. But actually, this theorem was not invented by Burnside. Actually, Cauchy was studying several coloring solutions. It was already raised up the corresponding theorem. Its foundation is actually the orbit theorem that we have mentioned just now. Therefore, this theorem is known also as the orbit counting theorem. Whereas this theorem is actually description means that corresponding to a limited group. For example, A1, A2 until AG. It is a G order of permutation group. Then each permutation can be written as a product of disjointed cycles. And this time, under our corresponding permutation effect, the number of the fixed point are also corresponding to each other. The number of one order cycle. We use C1AK to represent. G has 1, 2 until n number of multiple elements split into L order equivalence class. Then the number of equivalent classes L is equal to how many? It should be equal to the sum of the number of all one order cycles divided by the corresponding G order number, which is small g. Then let's look back at the starting point of this lesson. We have introduced the question: if we use red and blue two color to paint the vertices of the square, allow rotation, how many different color solutions are there? We can directly bring it to Burnside Lemma. Let's solve it. And this time, we first need to write out the permutation. There are a total of 4 permutations. If we assume that we are only considering rotations, then for each permutation, we can see that how many number of one order cycle are there. We can see that when it is under 0 rotation, there are a total of 16 one order cycle to correspond to the rotation of 90 degree to one order cycle, rotation of 180 degree for one order cycle, well, 270 degrees to one order cycle. Then we bring back to Burnside Lemma corresponding number of all one order cycle. Add them up, it is 16 plus 2 plus 2, 4 plus 2. Then correspondingly, how many permutations are there? Divided by 4, the answer is exactly 6. It is the same as what we have enumerated. And this time we will say that what does Burnside Lemma is trying to say. Corresponding to several images, we first need to consider the corresponding rotations. Which kind of operation mode should be, which is that we need to consider towards the rotation group of image set. Then corresponding to these images, we need to enumerate them all out. Then only we can see clearly its rotation effect. If we sort of using 10 colors, even 20 colors to color the vertices, and if it was no longer a simple square shape, it is even what we have seen over the blackboard, the cube with rotations. And this time we will realize Burnside Lemma still cannot nicely solve the space painting problem. Then in our next class, we will provide you with a detailed explanation.